A very good day to fellow viewers. I am Muhammad Irfan bin Izwan and my final year project entitled Static Impact Analysis to a Badminton Frame and Design Improvement. This is a simulation-based research using SolidWorks and ANSYS software. The flow chart shows the flow of the project, starting with the geometry, where 3D models were modeled in SolidWorks. Next process is meshing imported models in ANSYS Mesh. Then, the ANSYS mechanical static structure is set up, followed by solution where simulations were run in ANSYS mechanical structural analysis. At last, the results from simulation will be collected and calculated. But before getting into it, let's get to know about badminton. What is badminton? Badminton is a well-known racket sport. Do you recognize this man? Dato' Wirali Chongwei, or his predecessor and teacher, Dato' Misbah Siddiq. Both are Malaysian badminton legends, or Lindan, one of the all-time greats. The Yonex Lindan Voltric LD Force, named after him, is one of the most sought-after power racket to date. But then, do you know? There are countless types of racket to date. For starters, the oval and isometric head shape, the older T-joint, head-like balance, or the Yonex heavy head balance with hard shaft. There's also the Yonex Dora 10 with stiff shaft, which is one of the top power racket besides the Lindan racket mentioned before. You must be wondering what is all these different varieties of rackets, right? But don't worry, let's get to know the basics of what made up the main parts of the frame. From the top, consists of the head, which holds the string area. Then, moving down the throat, which connects the head and the shaft. Then, the shaft is connected to the handle, where we grip our hand around it and close it up with a butt cap. Next up, the problem statement is which parts of the frame will affect player performance in what way? There are multiple ways that racket design can influence the racket performance. The design parameters that should be put into focus to be improved also need to be determined. As for the objectives are to design racket that can improve the performance of player, and also to simulate static impact analysis on the improved design using CAD software. What are the parameters affecting the racket performance? Well, firstly, we have the material for the racket, either carbon fiber or aluminum or graphite. Material have to be fixed as this research focuses on design. So I choose carbon fiber as it is one of the most versatile material used for badminton frame while also maintaining strength. This is supported by a study done by Che Hassan et al. In 2018 using electron method. Next up, we have the two most dominant head shape in modern market, oval and isometric. The head shape will be further touched upon later. Lastly, we have the stiffness of the shaft. There is flexible and also stiff shaft, and there is a lot of degree for both settings, either high flexibility or high stiffness shaft. A flexible shaft racket can bend to a certain extent. The picture below depicts Dato' Lee Chongwei swinging a racket until its shaft bends after a big smash. The project follows the study by Nasruddin et al. In 2016. Figure 5 and 6 theoretically express the deflection of the shaft using the uniform cantilever beam system but with different designs tested. As for the formula, maximum deflection Ymax is equal to PL power of 3 over 3EI, where P is the concentrated force applied at the end of the frame, L is the length of the shaft, E is the modulus of elasticity for the material chosen, and I is the moment of inertia of cross-section of the shaft. As for the formula of stiffness, K is equal to P force over maximum deflection Ymax. Ymax value can be obtained from the simulation results. Figure 7 shows force applied at the top end of the badminton head in ANSYS software simulation. Table below shows boundary condition for this simulation, which is fixed end. At the bottom of the handle, the surface of the butt cap is fixed position, while force is exerted at the tip of the head. So, after understanding briefly the parameters, I plan to test the design improvement on the shaft radius and racket head shape. The radius of the shaft will be 0.6 cm at the handle, and the radius will decrease gradually to 0.4 cm at the throat or joint of the racket. I also plan to design racket with edges as it is supported by Liu in 2014, which stated Li-Ning company managed to create wind racket with sharp edges, which isn't possible before due to advancement of technology of shaping the carbon fiber. But previous simulation-based study only tested the normal oval, round, and isometric shapes, not the new shape with edges. Next, we move on to the design process. Process of modeling the badminton frame comes first. Figure 1 shows a 3D racket model without string model in SolidWorks. Figure 2 shows a successfully imported 3D racket model with string in ANSYS software. Next one is Figure 3 shows a snapshot during designing process in SolidWorks, while Figure 4 shows structural analysis simulation running in ANSYS using the imported model designs in SolidWorks beforehand. I choose unstrung racket because the simulation that I am doing does not involve the string tension factor. Creating mesh with the imported models were successful. During meshing process, in figure 7.1, there were 4,976 nodes and 2,325 elements were created from meshing on the normal racket design. While in figure 7.2, there were 8,970 nodes and 4,468 elements created from meshing on the improved edge design. Last, in figure 7.3, there were 4,603 nodes and 2,161 elements created in improved shaft design due to meshing. Next, I proceed with the simulation results, starting with the simulation results for maximum deflection Ymax. Figure 8.1 is the normal head shape and 0.4 cm radius shaft simulation showing maximum deflection Ymax value 5.9939 mm, while in figure 8.2, the Ymax for improved edge design is 5.8796 mm. Ymax for improved shaft design is 3.2532 mm in figure 8.3. Moving on, simulation results for equivalent total strain, which are as follows. Figure 9.1 is the normal head shape and 0.4 cm radius shaft simulation showing equivalent total strain of 3.5452, while in figure 9.2, the strain for improved edge design is 3.6427. Lastly, in figure 9.3, the strain for improved shaft design is 2.7197. Moving on, lastly is the simulation results for maximum principal stress. Figure 10.1 is the normal head shape and 0.4 cm radius shaft simulation showing maximum principal stress of 6.9213 MPa, while in figure 10.2, the stress for improved edge design is 6.9156 MPa. Lastly, in figure 10.3, the stress for improved shaft design is 4.3467 MPa. Next up, I'm going to show some of the video animation obtained from the simulation. As you can see, the Ymax of the improved shaft design is significantly lower than the normal design, and this is the same goes for the strain on the normal design and improved shaft design simulation. The tabulation of results is shown in table 1. Structural stiffness K is calculated and the results were listed. Here, we can definitely see that the racket with improved shaft design clearly outperformed the normal design in all parameters from the maximum deflection, strain, stress, and stiffness. The simulation videos we saw just now also shows the lower strain in the area around the throat in improved shaft design. The difference is very significant, while the improved edge design only slightly loses and lagging behind in the strain data, but but still, the edges improvement is actually aimed for creating a larger string bed area, which is not the focus of the study here, and better aerodynamic. So it is still considered a plus, as it also improve in decreasing the maximum deflection and stress on the racket. In deformation testing, the stiffer the racket, the higher the coefficient of restitution, the higher the speed and precision of the shuttlecock. So the player performance also increases. A stiff badminton racket should be more suitable to a novice and advanced player. Thus, it is not recommended to amateur and a new player, as it can cause injury. Chart and the graph shows the differences more clearly. Lower Ymax stress and strain results in higher stiffness. Racket with improved shaft design is the most stiff out of the three. Although the stiff racket can improve player performance, as mentioned before, stiff racket is actually not suitable for beginner because wrong stroke technique can cause injury. The edge design has similar properties as the normal design, but it has advantages due to the increase in bed string area and better aerodynamic, referring to the study by Liu in 2014. From the data collected, I can conclude that problem statement in determining what parameters affect design of the badminton frame is solved as the maximum deflection, stress and strain can be reduced in the new design, hence improving player performance. The badminton models were successfully designed as there were no problem during meshing process. The simulation of static structural analysis was also successful. And lastly, the research successfully achieved objectives and solved the problem statement. With that, I end my presentation here. Thank you for listening.